Hello everyone, I am Pooja. In this video, I'll be walking you through the 5th lab program, that is Design a Verilog program to implement decimal adder as a part of the digital design and computer organization lab. First, we will look at the concept of a decimal adder and its working mechanism, then move to the step-by-step code implementation and explanation. By the end of this video, you will have a clear understanding of how to execute this program in your lab environment. Let's get started with the overview of the decimal adder. Decimal adder is a circuit which is used to perform addition on binary coded decimal, that is BCD numbers, which represents decimal digits in binary format. In BCD, each digit is typically represented by a fixed number of bits, commonly 4 bits, making it a 4-bit binary code for each decimal digit, which lies between 0 to 9 range. However, unlike the standard binary addition, BCD addition has a unique constraints because the result must remain a valid BCD digit, that is 0 to 9 per digit position. Now, let's understand the working mechanism of a decimal adder. First step is providing inputs. Two 4-bit BCD numbers, example A and B, and a carry input, that is Cin, from the previous lower digit addition is given. Second step is performing binary addition. Under this, add the two BCD inputs, that is A and B, along with the carry input using a standard binary adder. This addition can result in a binary sum ranging from 0 to 9. Third step is to check for the valid BCD output. As the valid BCD digit ranges from 0 to 9, if binary sum falls in this range, no adjustment is needed. If the binary sum exceeds 9, then the result is invalid. So the solution to this is step 4, that is add a correction factor. To correct invalid BCD results, add 6 to the binary sum. This brings the result back into the valid BCD range and produces a carryout if required. The final step is output the result. The corrected sum becomes BCD digit for the current position. If a carryout is generated, it is propagated to the next higher BCD digit position. Now let's understand this with example. In the first example, we are performing binary addition by taking two inputs A and B, where input A is 6, that is 0110 in binary, and 9 as 1001. Then, by using the standard binary adder, the sum of these two is 15. Since the sum is greater than 9, we need to add 6 to the result to correct it. So let's add 0110, that is 6, to the 15, which gives the sum 10101. Now split the result into two BCD digits. The result obtained is 15, as the first digit when splitted is 1, that is 0001 in BCD, and the second digit obtained is 5, that is 0101 in BCD. Hence, the addition of 6 and 9 in BCD results in 15 in decimal. Let's consider the second example by providing input A as 11 and input B as 9. In BCD, each digit must be less than or equal to 9. The result which is obtained now is invalid because the second group, that is 1010, represents 10, which is not a valid BCD digit. So to correct this, we should add 6, that is 0110, to the previous sum. Then the corrected result obtained is 20 in BCD. Now let's move to the step-by-step code implementation by using the 64-bit project navigator. First, open the 64-bit project navigator, then click on File, then New Project. We provide the name as Lab 5, then click Next, then select Spartan 3 as a family name and finish. Then your project name appears. Click on that. Now New Source, again a tab opens. Here we should select Verilog module Then provide the file name as decimal adder as we are performing decimal adding. Then finish. Now click on the file name, that is decimal adder, and let's start to write the code. Here we are providing the inputs, that is A, B, and the output is stored in sum. The inputs are given as input 3:0 A, input 3:0 B. These declare 4-bit input A and B, assuming each input represents decimal in BCD format. Output 4:0, which is stored in sum. This declares a 5-bit output sum, which is expected to store the result. The extra bit is to accommodate a carry in case of the sum overflow. So let's assign sum is equals to A plus B. Now this line performs the addition of A and B and stores the result in sum. Here addition is performed in binary, but in context of BCD, this effectively represents the addition of two BCD numbers. We should check whether this code is free of errors in the file name and click implementation. Double click on check syntax. Process verifies that the code we have written is free of errors. We can execute as the green tick mark appears, suggesting no errors in the program. Now click on simulator to simulate the program and double click on simulate behavioral model. This takes a few seconds to provide the output screen. As the output screen appears, we have to adjust the output to microseconds. Now the screen is set to microseconds, and let me give the same inputs that I have considered in the example to check the output sum obtained. So click on input A, force constant. As the BCD is inherently unsigned because it focuses on representing digits, that is 0 to 9 in binary form, we have to provide the input in unsigned decimal. So click on the unsigned decimal and provide the value for A as 6 and click OK to apply, so the value gets updated to the input A. Now to provide input B, follow the same steps. Click on B input, force constant, then convert to unsigned decimal, and now provide the input as 9 and click OK to apply the value. Now on pressing the run button, the output appears, that is 15, as we have discussed in the example. We will give the value of our second example and check the output whether it is correct or not by following the same procedure. Hence, it is verified as the output is 20. In summary, this Verilog module is a basic building block for two BCD numbers, taking two 4-bit BCD numbers A and B and producing a 5-bit BCD sum. This is how a decimal adder ensures accurate decimal arithmetic, and these are essential in calculators and systems requiring decimal arithmetic.